Hey guys, welcome to Systems Design Fight Club. I'm going to try to do a quick run through of designing a search engine. Let's go ahead and just hop straight into it. So for resources on this problem, we've got Alex Shu's first book actually covers it. We actually have some coverage of it in Grokking, the systems design interview. And there is actually also some brief coverage in at least the Java edition of Elements of Programming Interviews. Which is a great book that's typically for coding questions instead. And also a great white paper for this is actually the Pregel one. Google actually created their own batch processing handling thing for scaling up to the scale that MapReduce runs at for the specific data that it works on. So the Pregel white paper is actually pretty solid for one specific aspect of the system design problem that we're going to cover. All right, for functional requirements, we are going to scrape links and web pages from the internet. We're going to present link recommendations when users provide some text input. For example, they'll type in GDP and then it'll provide some link recommendations for where to get gross domestic product information. So stuff like the Federal Reserve's statistics and stuff like that. Non-functional requirements, we're going to prefer high availability. It's okay for the data to be a little stale just by nature. This is a search engine. So when you type in the words, it's not actually going to do crawling and then get back to you. That would be really slow. So it's not going to have the latest links and information presented. So that means that we are going to have stale web pages presented to the users. And so that means that we are erring on the side of high availability, not high consistency, of course. So out of scope, we are not going to cover how to make it do autocomplete. We're not going to cover analytics on the queries themselves, which is the click-through rate, which is something that you really care about if you're doing AdWords. Those are probably also useful for prioritizing the links in the search results, although I think PageRank mainly goes off of just the number of inwards pointing links and outwards pointing links or something like that. We're not really going to cover robots.txt or this thing called politeness, which is making sure that we don't just absolutely hose Wikipedia with 1,000 requests per second. Okay, so let's get to the numbers. These are a mix from Alex Shu and Grokking. And actually, I think I kind of used, this guy had, I think, 10 billion web pages as the thing. I did my own thing here where I'm doing 3 billion per month, and I'm not just recrawling the entire internet every month. The web crawler for Google actually does a thing called adaptive learning or something kind of like that, where it's not recrawling every page at the same rate. It'll crawl like CNN at a faster rate than, let's say, some random web page, static web page that you spun up for a school project and it managed to index properly, and then you only touch it like once a year or something. It's not going to be crawling that as often as like CNN. We're going to have 2 billion daily active users for the reads with an average of 5 queries per second. Nobody actually provided that information. I actually just kind of grabbed that myself. This is actually going to come out to a pretty accurate number from the research I did for finding good read TPS for this problem. Nobody provided this. I'm not sure if we're actually going to get around to using it. I didn't run through this problem a lot beforehand, but I'm going to say that the average number of characters per URL is 100. The max is actually 2048. You can actually not make a URL or try to visit a URL that is over 2048 characters long. That's a hard-coded cap into just how GET requests work. Okay, so we can go ahead and try to calculate what's our write rate going to be? What's our read rate going to be? Wow, I used the wrong one there. What bandwidth will we need? That's specifically on the crawler side. That would probably be an interesting question on the read side too, though. And how much storage do we need? Okay, so for the write rate, that's going to be for the web pages getting recorded. So we have 3 billion pages per month. There's 30 days in a month. So we're going to do 3 billion divided by 30 pages recorded per day. So that would be 1 billion divided by 10, 100 million per day. And then we want to divide by 100,000 for the number of seconds in a day. That's for writes per second. So that will be 1 million divided by 1K. So that'll be 1K writes per second. So we're going to be recording 1,000 web pages every second. What's our read rate going to be? So we have 2 billion daily active users, and they have an average of 5 reads per day. They do 5 queries per day on average. So that's the number of queries per day. So that'll be 10 billion queries per day. How many per second? 10 billion divided by 100,000, the number of seconds in a day. That'll get us number of queries per second. So that'll be 10 billion divided by 100. We have 1 billion, 100 million divided by 1K, which is equal to 100K queries per second. And that is actually roughly how many reads per second Google.com really does serve. I actually came up with these numbers that'll come out to roughly what they do actually see from what I've seen on the internet. So 100,000 reads per second, 1,000 writes per second. I made that number up completely. It's loosely based off of the things I got from the other sources like Grokking and Alex Shu. All right, so what bandwidth are we going to need? So we're just going to focus on the crawler one here. So we got 1,000 writes per second. It's 100 kilobytes per web page. So that'll come out to 100 KB times 1K. So that will be 100,000, or we can do 100 megabytes per second. Yeah. That's equal to 0.1 gigabytes per second. I've usually seen internet speed measured in gigabits instead of gigabytes. That'd be 0.8 gigabits per second. And for reference, the EC2, using the general purpose ones, M5's latest edition, and that has about 0.75 to 2.5 gigabits per second. Just without any add-ons or anything. So you can handle that with 1 or 2 general purpose machines just off of AWS EC2 instances of this. So it doesn't look like we're actually going to be bandwidth bound here. It looks like this is actually not going to take up a lot of bandwidth to pull down those web pages because it's only going to need 1 to 2 machines for that. How much storage are we going to need? So we have 20 billion web pages. And they're 100 kilobytes each. So we're going to do 20 billion times 100 KB. That equals 2,000 billion. All right, hold on. 2,000 billion kilobytes, or it would be 2 billion megabytes, 2 million gigabytes, 2,000 terabytes, 2 petabytes. So that's a pretty fair number of hard disks that you're going to need. I think you can have more than 2 terabytes to a hard drive, but that's like an easier number to. I think it's pretty reasonable to have 2 terabytes to a hard drive. I don't know what the max could be on that. Maybe 100, which would mean that you would need 20 hard disks. So I'd say 100 might. I don't think you can put a whole petabyte on a hard disk. I've never heard of that. So I think we're gonna need at least, let's say if you could actually fit 100 on there, that would be like a bare minimum of 20 hard disks. But I'm pretty sure consumer grade ones can go 2 TB, so it's gonna be somewhere between 20 and 1,000, I think. Yeah, 2 TB. So that would be, yeah. So that was a range from 2 TB to 100 TB per HDD. Comes out to 20 to 1,000 hard disks. You're probably going to have something a lot more in the neighborhood of this. Google Dremel is actually set up such that every user of BigQuery actually gets about 1,000 hard disks like made available to them. So that's not actually, it's a normal number in the sense of the scale that Google operates at, but it's, that still is like a lot of hard disks. Yeah. Okay, so we can go ahead and jump into the problem now. So we're going to need to have some task runners. Let's start off with the stream. We're going to have a message broker that delivers some URLs. This is the URL frontier if you've looked through the resources at the top. So we're going to have a URL frontier. It's the stream of URLs. And we're going to be delivering them off to some task runners that are going to make some calls to an external website. So we're going to have our external web page over here, just some external website. External website. Okay, so you've got this stream of URLs. You're going to pull something off of it. And then you are going to make a call to that external website. It's going to return the web page. And then you're going to want to, let's label this. We're going to call it scrapers. They're just scrapers. And then you're going to store that in a object store. Don't like that one. Yeah, okay. This will be the web pages object store. Okay, and then we're also going to have metadata for that. So we'll have another one, which will be the metadata store. Okay, so we'll first write over to the object store, and then we'll write to the metadata store. And then we're going to have another message broker that's going to send the data downstream for further processing on these two things. So we're going to have an arrow over to that. Actually, I have a better symbol that we can be using. Can I stretch it like that? No, I can't. No, I'm going to stick to the other symbol. Okay, so this is going to be a stream to further downstream processing jobs. Okay, let's go through this has a lot of arrows to it, which means that you're gonna have interesting partial failure scenarios. So one, pull message off URL frontier. Two, let's have it on the left. Two, scrape the URL. Three, persist the web page to the object store. 4, update the metadata store. 5, we are going to add a message to the downstream broker. And then finally, update offset of URL frontier stream. And this whole thing should be idempotent, so when you're retrying it, you're going to get the same result. And I'll go into the scheme of the metadata here next. That means we don't really have to worry about distributed transactions or anything like that. All right, let's dive into the metadata store really briefly here. So you're going to want to have the URL itself. You're going to want to have, I think, the S3 location. So that'll be something like that. s3-aws.amazon.com/my bucket URL. That's where you've stored it. URL is the actual thing you're crawling. So it'll be like wikipedia.com/system design or something like that. And you don't want to pass around the URL itself. You want to pass around a URL ID. It'll just be an int like 1, 2, 3, 4. That'll just be 4 bytes as opposed to passing around this whole thing. That'll be an average of 100 bytes, as I said above. So it's easier to pass this around than the link itself. Okay, and we're also going to have the timestamp of the last crawl. And that'll be in Unix epoch time, which will look something like that. And so when it's idempotent, it's this update of the metadata store. You first want to persist the object. Otherwise, you're updating the timestamp of the crawl, and then you're not actually putting the updated, you might fail the next step. You wouldn't actually have the updated web page in there. So that's why I want to have the object store first and then the metadata store. It's that then you're not accidentally updating the timestamp, and then something downstream is trying to fetch this updated web page where it's not actually going to be in there because of a partial failure. Okay. Yeah, let's keep going. So we're going to have some downstream processing jobs. One of them is going to be a link extractor. We want to find all the links that it points to. So we're going to have a link extractor. And then we're also going to want to have something that flattens it into a format that works well for, so this one is doing like a BFS style thing, while this one is creating stuff that will actually be displayable to users. This will actually like rank the stuff. This is the flattener. I'll just call it that. And so the general arc that this thing's going to make is it's going to kind of come out and up over to there. And then we're going to want to have, there'll be the web browser for the users. So that's the browser for the searchers. We'll have a backend supporting it. So it's the search backend. And so they're going to make a request to that, and then they'll get their response back of a list of links. And so why did I go on this tangent? It's because that's where the flattener goes. The flattener is just going to head off over to there instead. So we're kind of creating some byproducts here off of the flattener, while the other thing's just going in this big loop around the system and collecting more and more links to send to the flattener, which will create byproducts to service to the actual thing that's exposed to external users. Okay, so we got this. They're both going to consume off of that, and I'm just kind of viewing these as Lambda functions. That's what we'll have them do. They're just kind of Lambda functions. They have they're receiving a message ID of just the URL ID. That's all we have in the message instead of the full link. Should be 1, 2, 3, 4. Okay, so the link extractor, it receives that, then it's going to call the metadata store first, find the actual URL or the S3 location. It's going to find that, and then it's going to pull the actual web page down, and it's going to pull a bunch of links out of it. And then I think we can go ahead and have it also do, so it's going to do a read. Should actually have these going the other way so that it's more of the data flow instead of the request response. So the data is flowing into the link extractor from the metadata store, but it's making a call to that. This is calling that. This arrow just indicates the data flow. And we're also going to have the data flow from here, because that's where it's going to get the actual links from. And then we can go ahead and we can actually have it just write directly to the metadata store, and if it finds a new link, it can actually just go ahead and set the timestamp of 0, meaning it was, so Unix epoch time of 0 is like 1987 or something. So if you have a new link, you would just have like, you would have URL ID 1235, and you would just set the timestamp to 0. It's like, okay, we're going to need to call that again because it looks like we haven't called it since 1987, which is fine. Yeah, so we're going to do a write back to this, and then I guess we could have it, we could either have it go on a stream, or we're going to want to have something that is putting the URLs onto this stream. We're going to want to have some kind of worker that is like going through these and prioritizing what we need to recrawl. So it's the recrawl prioritizer service. It's determining when it's time to crawl CNN again, or when it's time to recrawl, you know, random static web pages or Wikipedia again. And it's going to be putting messages over here onto that. So it could be a batch job that is just looking straight at the metadata store. Or we could also have it taking links in from the link extractor. So the link extractor, when it finds 0, it could actually just go ahead and write that directly onto this stream of URLs over here. That could be one option. But what if that new link that it found is an obscure Wikipedia link? So we're not, I said I wasn't going to cover politeness at all, but it's like, what if that new URL we found was another Wikipedia page, and we don't want to, you know, pound Wikipedia with 1,000, you know, reads per second. Wikipedia.com/obscure subject. Okay, and so we could actually also have another store where it's storing domain level info. So it could track like the last time that we called Wikipedia, and it could also use that for prioritizing when it's time to call Wikipedia again. So it pulls data in from there, it pulls data in from here. And so then this thing is going to have stuff like a domain would be like, oh, like that. The domain is just wikipedia.com, say last visited timestamp as well. And this is going to be different. This is going to be for all URLs under Wikipedia. And this would actually also be a great place for having some robots.txt metadata. And I don't want to get into this too much. This is going to be a wonderful rat's nest of complexity all of its own. What was I trying to get at with this? Oh, do we want to have link extractor stick things directly onto the stream, or do we want to have it go to the metadata store first? I think we want it to go to the metadata store first for that use case where we find some obscure subject. We don't want to prioritize it ourselves. We want it to go through the recrawl prioritizer first, which will determine whether or not we should actually crawl it immediately. Yeah, so this is going to be some kind of batch job operating on that metadata store. Okay, and then we got this flattener. It's going to take this thing. It's going to take this. It's also going to have to fish it out from the URL ID from the metadata store. So it's also going to technically make a quick read off of that. So it's going to first read off this, fetch the full thing, and then we want it to, we probably want it to do some kind of flattening, or it'll put it into a format that's more digestible. It'll do some data cleaning. That's what it is. It'll flattener. It does cleaning, and it flattens the HTML into like an actual text thing. So it pulls out all the HTML tags and stuff. Cleans and removes HTML tags. It might do, I don't know if we want this to do IDF-TF or not. It might do IDF-TF, inverse document frequency, term frequency. and it's going to put stuff into here, but later we are going to have a batch job that runs the actual page ranking algorithm. So this is going to be the page rank workers. And whoops, I didn't realize it split like that. It's going to have these page rank workers, and we're going to have it take in this cleaned up work. And the page rank workers, it's intuitively you would think that MapReduce is basically what you're going to want here, but it actually would also it actually works on a graph database. Shoot, that was another thing I need to get into with the link extractors, that it also puts data into a graph data store for links, which it'll be a graph data store where each vertex is a URL basically. So you would think it's going to be MapReduce. It's actually Pregel is kind of like created for this use case. Is it's batch jobs on a graph. So I'll say I don't know if that's like publicly available anywhere. There's a couple of alternatives I think that were called out in DDIA in the batch processing chapter. Actually, that's probably a good thing to call out in the resources. Okay, so I also said that we're going to want to have a graph data store of links pointing to other links to links. Center that. I'm going to move it over here. And so that's going to be another byproduct of the link extractor, is it's also going to write over there. And then PageRank worker is going to look at that. They might also look at this flattened thing of the web pages. I'd assume that it's not just running straight off of the number of links going into it, because then you're just going to get the most popular web pages on the internet, as opposed to having them ordered by the actual words that are in the web page. So this will be an object store of flattened web pages. Let's make that a little bit bigger. There we go. Okay, and we have the PageRank workers, and then we're going to have another data store. So there's a lot of hops on this design problem. So when you're thinking about how this whole interaction works here, is that you're going to want something that actually has a mapping of a keyword to a list of links. So you have a keyword like GDP, and then you're going to want to map that to a list of links. Like one of them will be like Wikipedia. We'll have Federal Reserve website. Etc. And so this is the actual format that you will want for the search backend, because you'll get a query coming in like GDP, and then you would want to return back. It would be a list of URLs. And so what's most optimal for that is that you'd eventually want the data to be in this. This is a read optimized data format. So your request comes in, it'll check this, it'll return a response back of the list of URLs and give that off to the browser. And so the data is also going to flow. The PageRank workers will take data from these two data sources, the GraphDB and the object data store, and it'll stick it over in this, which is it's kind of like Elasticsearch. You could, it's I think even in API it called out using an inverted index. I don't know if you would actually want to use sharded Elasticsearch at this scale. You could probably get away with DynamoDB or Redis or just a key value store, because you're going to do the mapping from the word over to the list yourself, I think, at the scale that we're going to want to operate at. Elasticsearch will do the creation of the inverted index for you. But I think at this scale, Google is just creating the index themselves, and then you just have a mapping of keywords to a list of links. What if they search for something like what happened in February 2000 or September 2007 or something, or Walmart stock. What if they wanted to look up stock price of Walmart? So you literally have Walmart stock. So I think you would also want to have pairs or tuples. You would have tuples of words. You could do them sorted or something. So if they typed in Walmart stock or stock Walmart, it would sort them. And then you can just have it. So that way you don't need to have Walmart stock and then stock Walmart in the database. Do that. And then you would have a link, a list of URLs for that. But this would be the key is a sorted list of words off to a list of URLs. And you can even have Redis for caching. So this would, you could do, I think DynamoDB would work really well here. Is let's do DynamoDB, eventual consistency. It's uses a B tree, so it's read optimized. This is going to be getting 100,000 reads per second. And then it's actually going to get fewer writes per second than upstream, because this is also doing a batch job. So this is going to be much more read heavy. And then we can even have Redis for the most popular queries. And then what goes into Redis would actually come off of some analytics. So you would you could have an analytics. I said I wasn't going to cover analytics at all, but we could say we're going to have like an analytics data store would somehow be involved. And then you would have a batch job that determines what to stick into the Redis cache. And then we would have this Redis cache of most popular search queries. Hey guys, I totally just fat fingered a thing, and so we just lost about 5 or 10 minutes of progress there. Well, it was mainly just the cache, this little thing. So for the analytics part, for determining what the most popular queries are, every time that there's a search that comes in, it's going to capture that in the analytics data store somehow. And then we're going to have this this batch worker that's occasionally going to start up. It's like a MapReduce job or something, and it's going to take the data from here. It's going to determine what what the most popular queries are, and then it's going to pull those queries from DynamoDB, where we have the full links for those popular queries. It's going to pull those then in, and it's going to copy it into the cache. And then the way that this is going to get modified for the normal request workflow is that first it's going to check that cache, and then if it's not in there, then it's going to check DynamoDB. And since this is Redis, it's in main memory, it'll be able to find the queries just off of RAM, which is a lot faster than DynamoDB, which will have to go all the way back to the hard disk. And so that's why you check this one first. But that's how that works. I don't want to go into the details a lot more beyond that. But yeah, if an interviewer ever bullies you on how to make the caching part work, that's my best guess. All right, I think we can go on to some capacity planning stuff and actually use all those numbers that we were calculating at the start. Those aren't just to show off your math skills, as one guy put it. It's so that you can figure out the number of machines. Because in senior SDE interviews, you really do sometimes get an interviewer that's like, how many machines do we need for XYZ microservice in here? How many do you need for the scrapers part, or how many do you need for the recrawl prioritizer or this search backend service? You will actually get asked that, particularly at the senior level and at companies like Google. I've definitely heard that they like to ask for latency estimates or machine count estimates and stuff like that. So we're going to do that. All right, so we had some number calculations. Why did we do that? We have the write throughput. We're doing 1,000 writes per second. We found out, so where is that happening? That is over here. This is where we're getting the 1,000 operations per second. It's over here. We also did the reads. That was 100,000, and that is over here. Let me go ahead and write that. So 100K TPS over here. We'll go ahead and make that large, and we'll make it bold. Can I make it bold? Okay, I don't know how to make that bold. We're going to make it large, though. And then over here, we're going to do, I think I said 1K TPS, right? Yeah, 1,000 writes per second. That's what's happening over here. That's the data coming in and where the amount of volume you're going to get on all these arrows over here, while 100K is up in the top right corner. Okay. So this is going to need a lot more machines than the other one. So what are we going to be bound on with the scrapers? It looks like we're not going to be bandwidth bound because we found out that would only be about 1 to 2 machines. We're going to need a lot of storage on the web pages object store. This is where we're going to see one of our bounds is that we're going to need a lot of hard disks right here. So when I came out with 20 to 1,000 HDDs, hard disks, the place that we're going to see that is right there is, yeah, we're going to keep that large too. 20 to 1,000 hard disks right here on the object store, right there. We're probably going to need some more on some of the other aspects too, but this one is maybe on the object store over here we might need a lot. I'm not sure if this whole step is actually 100% necessary. Yeah, but anyways, this is where we're going to see the most need for all those hard disks. Okay, so this is not bandwidth bound, but there's no way that we can actually get 1,000 writes per second off of a single machine, I think. Usually I've only seen a TPS. I've only seen machines that can handle a TPS of maybe 100. In fact, on databases, a fair number is usually about 1,000 TPS for a database machine. And I don't think the scrapers are going to be written in C and super optimized like databases. So you might need like maybe 10 machines over here. I'm just going to ballpark it. It's probably going to be, I think, like CPU bound. Probably going to be like CPU bound. It's trickier to estimate this one over here. Because if it was bandwidth bound, which was what I was hoping for, it would have only been one. It's currently only coming out to 1 or 2 machines. Okay, and then over here we calculated 20 to 1,000 hard disks. I think there's tricks for network attached storage where you can keep the number of CPUs itself kind of low. We're going to need a lot of hard disks over here. I think with HDFS, if you implemented that with HDFS, it does actually use commodity machines instead of doing a network attached storage tricks. So then you would actually have a 1-to-1 correlation between hard disks and CPUs, and so you might actually end up with 20 to 1,000 machines storing all that stuff. And then also if you're using MapReduce for these things, you actually put the compute directly onto the disks. With the way that typically works. So then you would actually want to have all of your CPUs from these things actually are going to be directly on the same machines that host the hard disks. Okay, what else can we do some estimates on? So over here is where we get the crazier numbers for TPS. And so that 100K TPS, that applies to this backend, and it's going to be, so you wouldn't, the cache should hopefully be sponging up a fair amount of that TPS. Without that, you would actually literally be hitting your DynamoDB instance at 100,000 reads per second. And so if we went ahead and just kind of ignore this for a second, then that means that you would literally have 100,000 reads going into this thing every single second. And you definitely cannot get a single machine to handle that scale. And so you would need to scale it up to, I think it's fair to say 1,000 TPS on one machine. So we're going to say that this one would probably be about 100 machines over here. So you don't usually do capacity estimates with DynamoDB, but let's say that maybe it's running PostgreSQL or something, or I don't know. They still, interviewers still like to have capacity estimates. But I think you would need like 100 machines running whatever database software it is over here, because that would come out to about 1,000 TPS per machine. With Redis, let's say, actually, let's go ahead and estimate that Redis is sponging up 20% of our reads. So we're going to say 20% of our reads are sponged up over here that would come out to 20K TPS being handled by Redis. And then that would mean that 80% of our reads then also need to go over here. So this would actually get, it would actually see 100% of the reads. It would still get hit 100 with 100% of the reads per second, but it's only 80% that make it the rest of the way through to DynamoDB. So then 80K TPS actually hit here. So that's just the sponged amount that don't make it to DynamoDB. And so then we would only need 80 machines. This one is still going to need to scale all the way up. I think Redis can handle a lot more TPS than anything that's going to have to look all the way at the hard drive. Let's say it's, I think somebody had recently posted a link that can help a lot better with capacity estimates on it. But I'm going to say it runs at least 10 times as fast. So maybe it can handle 10,000 transactions per second. And so then we would only need like 2 machines running Redis. At 10K TPS per machine. That's my best guess. Okay. And then the back end over here. I guess we could take a shot at seeing if this one's going to be bandwidth bound. So let's say that each of the URLs lists is going to be 10 URLs. And so we have 10 URLs per request. Each URL is 100 characters, so that's 100 bytes, so 0.1 kilobytes, and 10 URLs on each request. So each request is 1 kilobyte of URLs. If it's just 10 URLs, not any extra crap on it, like it's going to be JSON. So I mean, it's probably going to be a little bit bigger than that. We'll just keep it at 1 kilobyte to keep things simple for now, not get into too many details. And we're going to be handling 100,000 TPS. So it'll be 100K requests per second at 1 KB each. So we're going to do 100,000 times 1 KB. So then that would be 100 times 1 megabyte, 100. So then that is 100 megabytes, or 0.1 gigabytes, which is 0.8 gigabits per second. So still, that's not really impressive. That's something that one machine can handle. But I don't think you can literally handle. I've never seen 100,000 TPS off of a single machine. I think it's more realistic to have maybe 100, maybe 1,000 at most, but you're going to need like at least 100 machines over here on this backend service. Another thing I hadn't gotten into is that you should probably have a CDN for the static. When you load up google.com, there's a bunch of HTML and stuff that you need to see. So that would be a static asset on a, I'm just going to go ahead and have a box, and I'll say CDN. And that is what you're going to hit first. And then they'll be able to type in stuff and it'll hit the actual backend. Otherwise, you'd have a lot more bandwidth getting added to the search backend. Okay. I think those are all the most interesting numbers that I can think of that I actually know how to estimate. I'll go ahead and post this diagram in the Discord channel, and also the text file, of course. We had some useful resources up here. Thanks for watching. I'll go ahead and end the video. Thanks.